Hi everybody, so my talk is preventing you from lunch. I'm currently working at JPL, but all the work I present here was done previously doing my PhD at the University of Bern. So we mainly focused the last years on cometary ices, so this was more like a byproduct on the way to do experimental work on comets. So the motivation for this is like, what can we learn about the nature of plume particles and their deposition by analyzing photometry phase curves or polarimetric data? And can we distinguish older and younger depositions from plume particles? And of course, photometry is one way to bypass the pixel resolution problems of remote sensing, because we can really focus on one pixel at different angles and try to retrieve some additional data. And maybe to answer the question just asked before, can deposition explain thermal anomalies? So what type of sample material were we dealing with? Of course, we are not expecting like terrestrial snowflakes, because they have to evolve quite a long time when condensating from the gas phase. And all the data from Enceladus or Europa surface suggest that the surface is not consisting of such highly regular particles, because it's too much backscattering on the satellite. So what we expect are more or less spherical particles in the micrometer range, or as shown here, spherical particles with crystallization on top. These are flash frozen brine spheres where the salt crystallizes on top. So we developed in the previous years a bunch of different production methods for such tiny ice particles. The original one was mainly done in Braunschweig. This is a commercial medical inhalation device that produces a fine nebula that we directly guide in liquid nitrogen and create such 3-micron particles. Then you have some other ones mainly developed for higher production rates for cometary experiments. This one is ultrasonic, where the vapor is frozen inside a chest freezer that is cooled down to -80 Celsius. This one is ultrasonic, directly spraying in nitrogen, and here as well. This is a system where we can adjust the flow rate from a peristaltic pump plus a compressor, so to adjust the grain size. But compared to this read, this one has a very broad size distribution, which is quite hard to control. So now to sintering. So what is sintering? I think most of the people experience this already when just touching snow in winter. When it's fresh, then it's soft, and with time it gets harder. So I will mostly refer to thermal sintering in my talk, and not to other mechanisms like high-energy electron sintering that was proposed by different authors. So mainly sintering is a morphological change of material driven by the decrease of total energy of the system. So the surface area of the system is decreasing, and thus the energy. The timescales are mainly influenced by the temperature, of course, by the pressure environment, by the humidity in the lab, and as well by the grain size. So the smaller the grains, the faster they sinter. So I continue here. In this regime of grain sizes, we are mainly dealing with two different processes, mainly evaporation condensation between grains and surface diffusion. Plastic flow or volume diffusion does not really play a role in this regime. There is quite little data about quantification of these sintering processes. There is some older data, for example, from Maino and the Ebinuma from 1983, where they did some work, and the red ellipse here shows the regime where we did our lab experiments in Bern. So it's quite a narrow stripe in terms of temperature because you were restricted by the instrumentation. And the so-called neck radius is the radius of the connecting part compared to the radius of the particle. So here's an example that we published in 2015 with the method that creates this 4.5 micron particle. So this is just after production. We see the particles in a gray SEM, the pure particles plus here some frost condensation. Then when leaving them for 1 hour in a normal chest freezer at -40 Celsius and at atmospheric pressure, they already start to grow together. We see here these bonds where particles grow together and create this compaction, and of course now the surface area is smaller than before. When we leave the particles for a night, they get completely irregular, and what we see as well is that here the surface is really smooth, and what we see here is that it seems to sublimate from the surface, condensate in the neck region, and create this very irregular honeycomb-like structure on the surface of the particles. So what changes by sintering is mainly that we create these optical bonds that allow photons to penetrate deeper into the surface, because the number of scattering processes is reduced when they can more transmit through these bonds. The shapes get more irregular from spherical, and this is highly important when doing numerical modeling on light scattering, because most people do them on regular shapes because it's of course easier, but it gets quite difficult when leaving them for a long time. And we assume that as well the thermal inertia changes and the conduction as well, but we assume that it increases with time because there's more contact surface on all the particles and therefore a higher conduction and inertia. This would contradict a bit what we heard just before, that this fallout region have higher inertia than the surroundings. So now to the photometric data. So in photometry we usually deal with bidirectional reflections. So we have illumination from the sun on a spot on the surface, and we observe under a certain angle with the spacecraft, and the angle in between is the so-called phase angle. And when you go on the emission angle, usually we have like an incidence direction where the sun points. This is the backscattering point, and then in the other direction there is the forward scattering. And what we usually see on icy surfaces is like a so-called linear part, and then the so-called opposition effect. For example, here this nice image from Cassini showing on the Saturn rings. This is created by two different mechanisms that cannot really be distinguished. One is shadow hiding by surface texture when illuminating at a non-perpendicular angle, and the other process is coherent backscattering. It's mainly influenced by, of course, the chemical composition and the corresponding albedo, and it's highly sensitive to porosity and the macroscopic texture on the millimeter to centimeter level. It's not really sensitive to particle size and shape. polarimeter data is like the opposite. This one is really sensitive to particle shape and size, not as much on composition. So in polarization, we have unpolarized light from the sun hitting an object and then analyzing the polarized light from this source. And here the negative polarization we see, this is called a negative branch of polarization. It's like an opposition effect, like going in the other direction. We see it very similar, but the opposition effect has its maximum usually at real opposition, and in polarimetric data we see that this maximum usually lies at 2 to 4 degree phase angle. Just a short part about the instrumentation. In Bern we have a photoradiogoniometer in the visible and near infrared. This one is equipped with a semi-transparent mirror that we can measure exactly at opposition. It's quite hard to calibrate, but it works. It's sitting in a big laboratory freezer at -35 Celsius, so it's quite warm compared to outer solar system, and we are working at ambient pressure. The other instrument is a improvised polarimeter. It's a very similar design with 2 arms and acquisition sensor. Here it's not in a freezer, but just a bath of liquid nitrogen with a cooler compartment, keeping it at a low temperature. So what changes in terms of photometry by sintering? The most obvious change is that all surfaces tend to be more forward scattering when sintered. So when having opposition here, in the very beginning they are highly backscattering, moderately forward scattering, and with time this curve turns. This is only visible when illuminating at a certain incidence angle. It doesn't work for vertical illumination. When illuminating vertical, what we see is that the overall reflectance decreases with time, and this is this effect of that photons travel deeper and there's more absorption compared to a reflection scattering on this surface. Then another effect is that we decrease the amplitude of this opposition effect. It's quite subtle. It's not obvious on the first glimpse, but when analyzing like the extrapolated point here from the linear part as a ratio to the maximum, we see this decrease over time with a certain error bar, but it's obvious that, and it goes on for tens of hours. So there's no steady state or plateau reached after a certain time. This would go forever until it's like a solid block of ice, I guess. But the most prominent effect is really within the first minute or hour. So it goes quite fast at these temperature conditions. This just to compare our lab data to Enceladus and Europa. Enceladus is the most backscattering surface known. Europa is a bit less backscattering. Our tiniest ice particles are somewhere close to what Europa does in the fresh state, but when sintered it's highly forward scattering, more similar to a snow frost or a newly fallen snow on Earth. Now in polarization, what we see is that the negative branch of polarization is highly dependent on the grain size. So the smaller the particles, the more negative the polarization is. and that after a certain size it gets more or less stable and is not really distinguishable from irregular particles of crushed ice. But what we learned quite recently is that we can distinguish ice particles created from the vapor phase and ice created from the solid liquid phase. When we measure frost condensation on the surface or on ice, we always see this Disglory effect in polarization. This is when the frost nuclei are still spherical and don't have this dendritic structure that frost usually shows after a certain time. And this difference comes from the internal structure. So frost condensation are more or less transparent, while flash frozen liquids have impurities. And these impurities prevent this Disglory effect, because the liquid starts to freeze on the outside and freezes towards the center, and thus creating stress and fracturation inside the particles, making them more opaque. So in polarization, what you see by sintering is that this minimum of negative polarization changes with time. The linear part here is slightly bending over time, but not as prominent, and it's quite highly wavelength dependent. So what are the problems? Our particles are strongly correlated to porosity. So the smaller particles we create, the more porous are the samples, because the surface sticking forces are so high on these small particles. And we are not able to produce and measure amorphous ices in these facilities because the temperature is just too warm. We don't have any data yet for salty ices. We assumed that maybe the timescales of this sintering effect could change a bit, but it's still unknown. So to summarize, observation at a very low phase angle are crucial to see this sintering effects. Additional observation at high phase angle, like more than 100 degrees, are favorable to detect this forward scattering behavior. So photometry and polarimetry are sensitive to very different characteristics and so complement each other in terms of porosity, grain size, grain structure. Of course, we should not forget here spectroscopy that allows to make some assumption about the overall grain sizes. So what has to be done in future is some quantitative studies under relevant conditions for Europa or Enceladus that are still missing. Thank you.
Is this working? Yes, it is. So really nice work. This ties in very closely with some work I've been doing at JPL with Jamie Malaro, who's doing sintering modeling, trying to understand the mechanical properties of potential surfaces on Enceladus. Our modeling suggests that on Enceladus, the rates of sintering are extremely low due to the low temperature, and that you don't get much sintering because of the progressive deposition on the surface. The deposition rates exceed the rate at which you can at least densify due to sintering, which I think is somewhat relevant here. But a piece of data you might not be aware of is that the microwave observations of Enceladus, so with the Cassini radar, suggest backscattering enhancements relative to the equivalent of Lambertian of about a factor of 3 or 4. Now, coherent backscattering can fairly easily explain an intensification in backscatter of a factor of 2, but when you go beyond that, that suggests there's some sort of macroscopic structural basis or something like interesting Mie scattering processes. I'm not sure what's really going on there yet. That is not just to do with the microphysical grain sizes. And so you might want to consider that in any modeling, that there may be some facets pointed into the observation, some sort of weird structural variation going on there in Enceladus as well. But I invite you to perhaps come and meet our group, and we can have a more detailed discussion about it at some point.
Cool.
No, this is very interesting. Do you have any plans to do NIR spectroscopy measurements with these sorts of systems, or is that?
Yeah, currently at JPL I'm doing dehydration kinetics of hydrohalides, but I do as well this very small grained ice particles. I worked already on this.
Okay, well, maybe this is best done offline. Like, how thick of a? I'm just wondering how deep of a population do you have in these sorts of systems? Are they many particles thick, or just a few particles thick, or?
So the samples?
Yeah, the samples.
They're optically thick. So in Bern we're dealing with centimeter-sized samples.
Oh, awesome. Okay, cool. Thanks.
It's great work. It's really, really interesting. I had a question, kind of hypothetically. Just wondered if we had a lander someday that goes to Europa and can scoop up a chunk of the surface, is there a way that you could tell from the grain characteristics of the ice particles whether it was a plume deposit, how old the plume deposit was, say, by thinking about the sintering processes that would be occurring? Just wanted your thoughts on that, I guess.
So this light sintering is really hard to detect because the mechanical strength is not changing a lot. It's very subtle. For example, this image after 1 hour, by eye or just by probing, you cannot distinguish from fresh samples. Of course, after tens of hours, it's really getting a crust and getting hard. This we could detect. I think the best indication for plume deposits is when we would find round particles that are still spherical. So this means that they would be quite fresh, not heavily bombarded by electrons or micrometeorite. So
can you quantify a little bit fresh? Like what would that, to what time frame would you say? Could you still say it was fresh?
This is hard to extrapolate in the conditions.
Okay, just curious.
Of course, we are magnitudes away in terms of pressure and temperature.
I'd refer you to a paper coming out by Jamie Malaro, who does some of those calculations for Enceladus. And we can scale them because it's all thermal effects in her model, at least. She hasn't considered electrons either, to Europa just by looking at the different surface temperatures. So I'd say that's probably coming out within the next 6 months.